What if I told you that to make our smartest AI models even smarter, we don't actually need a massive new supercomputer?
Right, and we definitely don't need to wait around for months for some hyper-intelligent teacher model to finish training.
Exactly. We basically just need two dumb models and a subtraction sign.
It sounds a bit crazy when you put it like that.
But it works.
Yeah.
This is AI Paper Slop, and today we're doing a deep dive into a paper that, well, it solves this massive impending problem in the post-training ecosystem. Because the industry is hitting a wall right now.
Yeah, the frontier wall.
Right, for years, the recipe for making a small model smarter was super simple. You take a massive, 235 billion parameter beast,
Yeah.
and you distill its knowledge down into an 8 billion parameter student.
But as our frontier models reach the absolute edge of current capabilities, there just aren't any bigger teachers left to distill from. You can't learn from someone smarter if you are the smartest one in the room.
Which brings us to today's paper. It's called Weak-to-Strong On-Policy Distillation, or W2SOPD. And it comes from researchers at the University of Maryland, Microsoft Research, and MBZUAI.
And the core insight here is just fascinating. They mathematically prove that an 8 billion parameter student model can learn from much smaller 4 billion or even 0.6 billion parameter models and actually surpass them.
Which feels like it breaks the laws of physics, or at least the laws of machine learning. They do this by subtracting the outputs of two weak models in Logit space. That isolates a pure capability direction, and then they inject that directly into the student.
I mean, for anyone working in alignment, this completely reframes the fundamental assumption of weak to strong learning.
How so?
Well, historically, distillation has always been framed as imitating a supervisor, right? But if your supervisor is weak, imitation is a trap.
Yeah, you just learn to be weak.
Exactly. So by shifting the paradigm away from imitating a weak supervisor and towards isolating and transferring a capability direction, it means our frontier models can keep improving iteratively.
Using the abundant, cheap, weak signals we already had sitting on our servers right now, we are just no longer bottlenecked by the need for a smarter teacher.
Right. And to really understand why this Logit subtraction method is such a huge breakthrough for ML engineering, we need to look at the specific bottleneck they are trying to bypass.
Right. The paper focuses heavily on policy distillation, or OPD. Now, for the technical folks listening, you probably know OPD is basically the golden child of post-training right now.
Oh, absolutely. It merges the best parts of our two main paradigms for improving reasoning.
Let's unpack those paradigms real quick, just to set the stage.
Sure. So the landscape of reasoning improvement is largely split. Over in one camp, you have reinforcement learning with verifiable rewards, or RLVR.
Which is incredibly powerful.
It is, because it scales optimization directly from verifiable outcomes, like, checking if a Python script runs without errors, or if a math proof yields the exact right integer at the end.
But the reward signal there is notoriously sparse.
Incredibly sparse. Think about it. If the model generates a 500-step chain of thought, the verifiable reward only gives you a binary success or failure at the very end of all that text.
So the model is left completely in the dark about which specific tokens, back in step 42, were the brilliant logical leap and which ones were just total filler.
Right. It faces a massive credit assignment problem. It basically has to stumble blindly around the state space to figure out exactly why it got the reward, which is computationally exhausting.
Right. Which leads us to the second camp, which is knowledge distillation.
Exactly. Knowledge distillation gives you dense, token-level supervision from a teacher. The teacher tells the student exactly what probability to assign to every single word.
Which solves the credit assignment problem. But standard distillation relies heavily on off-policy trajectories, right?
Yes. You are forcing the student to learn from the teacher's generated text.
And that introduces exposure bias. The student learns to mimic the teacher perfectly in training, but out in the wild during inference, the student will eventually make a slight error.
And because it only trained on the teacher's perfect golden trajectories, it has no idea how to recover from its own mistake.
Right. It drifts into a state space it never saw during training, and the performance just totally collapses.
That is the exact mechanism of exposure bias. So on-policy distillation comes in to solve this. OPD says, let's use the student's own rollouts.
Okay, so the student autoregressively generates the text, entering its own natural state space.
Right, but we use the teacher to score those specific tokens, so you get the dense credit assignment of distillation, but it is safely anchored on the student's own distribution.
It sounds perfect, but OPD relies on two paradigms to actually work in practice, and they both kind of suck right now.
Yeah, they have huge limitations. You either need a strong to weak setup, where you distill a massive Quen 3 down into an 8B model, Or you use same origin consolidation.
Which is where you train multiple domain experts.
Yeah.
Like one for coding, one for math, and then you merge them.
Exactly. But both of those require a teacher that is at least as capable as the student.
And this is where I look at the current state of the art and just wonder how we move forward. I think of it kind of like a grandmaster chess player trying to improve.
Right.
The grandmaster can't just hire a better coach because none exist. And cloning themselves to spend 10 years studying only endgame theory just to consolidate that knowledge back into their own brain later. I mean, the compute cost of training multiple domain experts at a frontier scale is just astronomical.
It's completely unfeasible for most labs.
But wait, hold on. If standard distillation is about matching a teacher, and our grandmaster student tries to distill from an amateur chess player, basically a weaker model, I'm assuming standard distillation just lobotomizes the student.
Oh, you would absolutely lobotomize the student.
Like if I force an 8B model to minimize its divergence from a 4B model, doesn't it literally just learn to be dumber?
Yes. Standard weak-to-strong learning bounds the student's capability to whatever the weak teacher's ceiling is. And there are two mathematical reasons why this happens.
Okay, lay them on me.
First, there is a severe distribution mismatch. The weak teacher's distribution of tokens is completely distinct from the strong student's natural distribution.
Right, they just talk differently.
Exactly. The paper notes that this mismatch mathematically weakens the distillation signals, which makes the gradients noisy and largely ineffective.
And the second reason.
It's the capability ceiling itself. If your loss function is literally minimizing the reverse KL divergence between the student's logits and a weaker teacher's logits, you are directly penalizing the student whenever it tries to be smarter than the teacher. You are actively pulling it down.
Okay, let's slow down here because this is where the paper introduces a mechanism that feels almost like magic to me.
The Logit subtraction.
Yeah. Since a weak teacher actively drags the student down, how does W2SOPD actually transfer the knowledge without transferring the weakness?
They do it by operating entirely in Logit space. The core observation they make is that even if two models are weaker than your strong base model, the difference between them encodes a highly pure, transferable capability direction.
Okay, walk me through how this works under the hood.
Sure. You take a positive model, which we'll call M+, and a negative model, M-.
And both of these are weaker than the student.
Both are weaker. For every single token in the sequence, you look at their raw logits, Z+ and Z-. What they agree on represents their shared limited abilities and their general weaker biases.
Okay, I follow.
So when you subtract the negative model's logits from the positive model's logits, you mathematically cancel out all that shared weakness.
I was trying to wrap my head around this earlier, and it kind of sounds like noise-canceling headphones. Like if you have the audio you want, but there's a bunch of background airplane noise.
That is a brilliant way to visualize it. With noise cancellation, you use a microphone to record the exact ambient noise, the bad signal, and you invert the phase.
Right, and when you add that inverted phase back into your audio stream, the noise cancels out completely, leaving only the pure audio you actually wanted to hear.
Precisely. So here, you take a weak model that happens to have one specific skill, but it's full of bad model noise, it's general lack of intelligence.
Yeah.
You subtract a slightly worse model to isolate that bad noise, cancel it out, and you are left with a pure mathematical vector of just that one specific skill.
And then you inject that pure isolated skill directly into the massive student model.
Exactly. Mathematically, they take the strong student's base logits, which we can call Z-base, and they add that isolated capability direction.
So the formula is essentially Z-base plus an amplification coefficient, alpha, multiplied by the difference between Z+ and Z-.
You nailed it. And the result of this addition is what they call the proxy teacher.
But just to be clear for anyone listening who is, trying to implement this today, the proxy teacher isn't a real model.
No, it's completely synthetic.
Right. It doesn't physically exist as a standalone neural network living on your GPU that you can chat with.
It exists purely in math, calculated token by token during the training loop. And this is the crucial part. Because you are adding this pure capability direction directly onto the student's own base distribution, the proxy teacher inherits the new skill while remaining distributionally adjacent to the student.
I see.
Then the student distills this proxy teacher by minimizing the per token reverse KL divergence on its own rollouts.
Okay, but if I'm looking at a training loss curve and I just blindly add this isolated skill direction to the base model's logits, couldn't that distort the student's distribution entirely?
What do you mean?
Like, if I turn the volume up too high on that pure signal, doesn't it push the target distribution so far away that the student can't even learn it?
That is a very real risk, which is why the amplification coefficient alpha is designed entirely to prevent that collapse.
How does it do that?
Well, the paper views the proxy teacher as a product of experts over a shared vocabulary. The alpha parameter controls the strength of what we call a KL trust region centered at the student.
Okay, so think about minimizing KL divergence as forcing two probability distributions to match.
Right. If alpha is too small, say approaching 0, the proxy teacher stays way too close to the base model.
The capability direction is barely injected at all.
Exactly. And no meaningful supervision happens. The student just learns to be itself. Region entirely.
You push the proxy teacher far away from the student's natural distribution.
Yes. The target distribution begins to look completely alien to the student's base weights.
Do they actually test this in the paper?
They do. The paper includes ablation studies on the Quen 38B model showing that as alpha goes past 1.0 or 1.25, performance starts to degrade sharply.
Because the supervision becomes increasingly hard for the student to actually map its weights toward.
Exactly. A moderate alpha strikes the perfect balance. It forces learning without breaking the underlying distribution.
Okay, the math makes total sense to me. Subtraction isolates the skill, alpha keeps it safe. But if I'm an ML engineer implementing this today, where do these M plus and M minus models actually come from?
That's the beauty of it.
Because if I have to train a bunch of contrast pairs from scratch just to get these weak signals, this isn't practical at all. But the paper details 3 specific flavors of instantiations.
I do. The framework is incredibly flexible as long as you have a separable capability gap between two models.
So what's the first flavor?
The first flavor they test is pre-RL versus post-RL.
Okay.
Your positive model is a small 4 billion parameter domain expert that has been trained using RL. Your negative model is its exact 4B pre-RL initialization base.
Oh, wow. So to put the compute cost into perspective for you guys,
Yeah.
running reinforcement learning on an 8 billion or 70 billion parameter model is incredibly expensive.
Oh, it's massive.
It requires generating thousands of rollouts, scoring them, updating massive weight matrices. But running RL on a tiny 4B model is comparatively cheap.
Very cheap. So by subtracting the pre-RL base from the post-RL expert, you isolate the pure skill that RL instills.
And you transfer that highly expensive capability to the 8B student without ever actually running RL at the 8B scale.
Exactly.
That is remarkably elegant. You're basically doing the expensive iterative thinking on the cheap hardware, extracting the aha moment as a mathematical vector, and just handing it to the big model.
It really is elegant.
But I really struggle with the second flavor. Here's where it gets really interesting. The paper calls it smaller versus larger.
Right, the scale contrast.
They say the positive model is a 4 billion parameter base model, and the negative model is a 0.6 billion parameter base model. Wait, let me make sure I'm hearing this right.
Go ahead.
You're telling me I can just go to Hugging Face, download a 4B and a 0.6B open weights model, subtract them, and my 8B student gets smarter.
That is exactly what they're saying.
How does a 4B model inherently possess a skill just by being bigger? There is no new training data here, no reward design. This sounds like a free lunch. How does scale alone create a transferable capability direction?
It completely sounds like a free lunch, I agree. But the mechanics of emergent capabilities explain why it works, and the benchmark data absolutely backs it up.
Okay, explain the mechanics to me.
What you are isolating there is the capability that emerges purely from network depth and parameter count. A 4 billion parameter model has more layers, larger hidden states. It can build intermediate representations of logical steps.
Right, it can capture long-range dependencies in the text.
Exactly. But a 0.6 billion parameter model is physically constrained. It often acts more like a highly sophisticated and n-gram model.
Like memorizing surface-level syntax and common co-occurrences.
Right, but completely failing at deep logical deduction. So when you subtract the 0.6b's logits from the 4b's logits, you are literally erasing the shared just predict the most common next word bias.
Oh, wow. What remains is the pure logical deduction that only the larger parameter count could actually represent.
You isolate the benefit of scale itself and inject it into the 8B model. It requires 0 new training to get the signal.
Okay, that actually makes a lot of sense when you put it like that. You're filtering out the basic syntax prediction to leave only the deeper reasoning.
Exactly.
What about the third flavor? What if I only have one cheap base model and I don't want to download different sizes or train an RL expert? Am I just out of luck?
Not at all. And that brings us to the third instantiation, which is correct versus wrong hints.
Okay, how does that work?
This is highly efficient because it uses a single small base model, say a 4B model. The positive model is that 4B base, but in the prompt, it is conditioned on a correct solution hint.
Okay.
The negative model is the exact same 4B base, but conditioned on a wrong hint of an identical format.
Ah, I see. Because the prompt formatting and the model weights are perfectly shared, the Logit subtraction just cancels out the style shift.
All right, the formatting bias is gone. It isolates the pure instance-level direction toward the correct solution. It provides token-level supervision extremely efficiently using just one model.
Right. I need to see the hard data on this. Because the theory is great, but we need to know if it actually moves the needle in practice.
The benchmarks are very strong.
Right. We are talking about Quen 3.8b as the strong student. The benchmarks they use are rigorous. Math competitions like AIM 2024, AIM 2025, and HMMT. For code, they use HumanEval plus Lamble, MBPP plus RAN, and Live Code Bench.
All standard, very difficult benchmarks.
So let's look at the pre-RL versus post-RL setting. W2S OPD beats standard OPD by an 11.4% relative margin on math and 3.7% on code.
Which is a solid jump.
But here's the part that proves the whole premise to me.
Yeah.
The 4 billion parameter post-RL experts scored an average of 48.8 on the math benchmarks.
Right.
The 8B student-based model started way down at 17.0. Standard OPD pulled the student up to 46.5.
So to hit the ceiling, it remained trapped just below the 4B teacher.
Exactly. But W2S OPD pulled the 8B student up to 51.8. It completely broke the distillation ceiling. It surpassed the teacher it was literally learning from.
And this holds true across the board. In the smaller, larger, and the contrast of hint settings, W2S OPD successfully improves the 8B student, even though every single supervision source in the equation is weaker than the student itself.
This is wild.
It also proved highly effective for multi-teacher distillation. When they mixed math and coding training data and routed each sample to the corresponding small domain teacher, W2S OPD consistently outperformed standard OPD.
So it essentially merged the capabilities of multiple domain experts without the catastrophic forgetting or interference you often see in sequential fine-tuning.
Exactly.
Now, from an ML engineering perspective, if I'm spinning up a cluster of GPUs for this, what is the hidden cost? Because W2S OPD requires forwarding 3 frozen models during training, right? The 8B anchor, the 4B positive, and the 4B negative.
That's right.
You'd think that would absolutely destroy your throughput and basically triple the time.
You would think so, but the paper points out this only adds a 20% wall clock time overhead per step compared to standard OPD.
Only 20%.
How? Well, that efficiency is crucial for practical deployment. The most expensive part of any on-policy distillation is the rollout generation, where the student auto-regressively generates the text, token by token.
Right, doing that generation phase is super slow.
And both standard OPD and W2S OPD share that exact same bottleneck. The scoring passes on the frozen contrast pairs, the 4B models, are just forward-only passes on text that has already been generated.
Oh, I see. They can be parallelized perfectly across devices.
Exactly. You completely avoid the backpropagation bottleneck for the teachers.
Okay, but practically speaking, shipping logits across nodes is a nightmare for bandwidth.
Yep.
If you have a vocabulary size of 152,000 tokens like Quen does,
Yep.
and a sequence length of 8,000 and a standard batch size, you're moving gigabytes of FP32 logit across the interconnect for every single step. Your GPUs will just sit there starved waiting on the network.
That is a very real hardware constraint, which is why they implement TopK OPD to save on cross-node communication.
TopK OPD, so they just truncate it.
Exactly. The teacher workers do not ship the entire 152,000 token probability distribution. They only ship the top 32 token indices and their log probabilities.
And everything else is just treated as 0.
Right. This turns a massive, dense tensor into a tiny, sparse matrix, drastically saving bandwidth. And they estimate the KL divergence on that truncated support without losing any meaningful performance.
So we have the mechanics, we have the benchmarks, and we know the hardware overhead is totally manageable.
Yeah.
But I'm looking at these results, and I'm still stuck on one fundamental question here. If the student is surpassing the teacher, and it's improving from purely weaker models, what exactly is it learning token by token?
It's a great question.
Because it clearly isn't just memorizing facts. A 4B model doesn't know facts that an 8B model doesn't.
Right.
What is actually changing under the hood during the generation?
This is perhaps the most revealing part of the entire paper. They conducted a token-level analysis to see exactly what is being transferred.
How did they measure that?
At every position along a generated solution, they measured the log probability delta between the positive and negative models.
So the tokens with the highest delta are the ones most strongly reinforced by the isolated capability direction.
Exactly. They took the top 1% highest delta tokens across 200 math reasoning traces, and they classified them to see what the models were actually focusing on.
The paper mentions they use Schoenfeld problem-solving episodes to classify them. I'm vaguely familiar with this. Isn't that just the framework where they split mathematical reasoning into different cognitive phases?
That's the core of it. Yeah.
Like figuring out the overall plan versus actually crunching the numbers.
Right. Alan Schoenfeld's framework breaks problem solving down into reading, analysis, exploration, planning, implementation, and verification.
Okay.
And the fascinating part of this token analysis is that different contrast pairs reinforce entirely complementary reasoning patterns.
What do you mean?
When you use the post-RL and hint contrasts, the capability direction heavily emphasizes tokens related to the reasoning framework itself.
So metacognition.
Yes. We're talking about the tokens where the model is planning its approach, analyzing the problem state, and monitoring its own solving process. The small model learned how to think about the problem through RL, and it transfers that metacognition to the big model.
Okay, but what about the scale contrast?
When you use the scale contrast, subtracting the 0.6b model from the 4b model, it heavily emphasizes the actual solving procedure and the mechanical implementation steps.
Wait, let's unpack that. If I synthesize this, it sounds like these weak signals are acting like highly specialized assisting coaches for our grandmaster chess player.
I like that analogy.
One coach, the RL or the hint contrast, is sitting there saying, hey, step back, let's look at the higher level strategy. Are we planning this right? Let's analyze the board. That coach teaches the 8B model metacognitive planning. Meanwhile, the other coach, the scale contrast, is standing next to them saying, your strategy is fine, but your mechanical execution is slightly sloppy here. Tighten up the procedural steps.
Right. Focusing on the mechanics.
Neither coach is as smart as the 8B model overall, but because we isolate their specific pure advice in Logit space, the 8B model absorbs their distinct coaching without picking up their bad habits and becomes better than all of them combined.
That framing captures the dynamic perfectly. And it brings us to a final synthesis of why W2SOPD is such a critical step forward for the industry right now.
Yeah, it feels huge.
It really is. This paper proves mathematically and empirically that we do not need to wait for a massive, smarter teacher to be built just to improve our current frontier models.
The signals we need to break through the next wall are already there.
Exactly. They are hidden in the delta between the weak models we already have sitting in our repositories.
Which leaves you, the listener, with a rather provocative thought to mull over. If you look at equation 11 in the appendix, the paper views the proxy teacher as a product of experts over a shared vocabulary.
Right.
And we just learned that we can extract pure capability directions from any pair of models showing a capability gap as long as they share a tokenizer. So what happens if we start cross-pollinating across the entire ecosystem?
Oh, that's an interesting thought.
Could you take two highly specialized open source models, subtract their weaknesses to isolate a completely novel capability direction, and then inject that pure vector directly into a massive proprietary architecture?
Without sharing the training data.
Exactly. You wouldn't need to share the underlying training data. You wouldn't even need to retrain the base model from scratch. Could this Logit space alchemy be the key to securely transferring pure reasoning skills across the entire AI ecosystem without ever exposing the underlying IP? Think about it. Until next time, keep diving deep into the slop.